Hey class, and welcome back for the second part of chapter 2. I was going to say the second half, but this will probably be a little bit shorter than the first chunk because there's a lot of new material there. But now what I want to do is I want to take what we learned in the first part of chapter 2 in terms of kinematics and motion and equations of motion and apply them to things moving vertically up and down under the influence of gravity. So I want to start with kind of a simple conceptual question that is actually a little bit tricky. Imagine I have a coin, or actually what I do have is a little ball, okay? So I have a little ball, or you can picture a coin any way you want. But if it's tossed straight up and back down, okay? If you want, I can even make my picture big. Look at this fancy stuff, huh? So here's my ball. I can toss it straight up and it comes straight back down, all right? So as it moves, you can think of there being sort of three parts of its motion, right? On the way back up, at its very peak, and then on the way back down. Okay, so for these three parts of motion, I want you to describe for me what the velocity is like and what the acceleration is like on the way up, at the top, and on the way back down. So when I say describe, I mean think about things like, is it positive or negative or zero? Is it increasing or decreasing? Those sorts of things, or staying the same. Those sorts of things for both velocity and acceleration in those three portions of motion. Okay, so maybe go ahead, pause the video, and describe the motion in those three parts. Did you pause it for real? Pause it, try it out. Okay, let's talk about this together. So let's start with velocity. On the way up, the velocity starts positive but decreases, right? It slows down. So it's a positive but decreasing velocity on the way up. The instant it's up at the very top, what is its velocity? It's approximately zero because it stopped, right? If it was not zero, it'd still be moving up. And then if it was negative and not zero, it would have started falling. So at its very peak, its velocity at that instant is zero. Then it falls down, and so it has a negative and increasing in magnitude velocity as it returns back to my hand. Okay, so that's the velocity. What about the acceleration? Well, let's think about it. On the way up, the velocity is decreasing. So therefore the acceleration must be negative or in the downward direction. On the way down, the velocity isn't becoming more negative, it's increasing in magnitude but in the downward direction, so the acceleration must be down. But what about that instant when the velocity is zero? What's the acceleration then? Guess what? It's also down. So the acceleration due to gravity is actually the same for all three parts. It's a constant negative downward acceleration. Weird, right? A lot of people want to say the acceleration is zero up here. While the velocity is zero at that instant, it is still technically changing. The instant before it was positive, at that instant it's zero, and at the next instant it's negative. So therefore it's still changing. And so you have a constant acceleration during the entire motion. Weird, right? Well, this constant downward acceleration is what we refer to as the acceleration due to gravity. And when we have objects that are only moving under the influence of gravity, we call that free fall. And so we're going to be looking at and practicing with this idea of free fall quite a bit to help us better understand motion. All right, so the acceleration due to gravity is 9.8 meters per second squared, or 32.2 feet per second squared. Those are the magnitudes. The direction, keep in mind, is always down towards the center of Earth. So if I go back to thinking about my ball that I have here, right? If I were to release the ball and it falls for 1 second, if it starts at zero velocity after 1 second, it will be moving at 9.8 meters per second because its acceleration is 9.8 meters per second, or meters per second squared. So after 1 second, it'll be at 9.8 meters per second. After 2 seconds, it will be double that, so 19.6 meters per second, and so on. Every second, it will gain 9.8 meters per second of speed in the downward direction. And the opposite is also true. If I threw it up at exactly 9.8 meters per second, then after exactly 1 second, it would stop, and then it would fall back to my hand over 1 second again, and return to my hand at a negative 9.8 meters per second of velocity. Pretty interesting, right? So, okay, this sounds good, but it's a little weird, right? What I'm implying is that all objects fall at the exact same rate. That seems weird, right? If I drop a feather and a tennis ball, they don't fall at the same rate. If I drop a piece of paper and a rock, they don't fall at the same rate. So what's the deal? Well, the deal is that all of what we're talking about is assuming that there's no air resistance. We're assuming that we're in a world with zero air resistance. And then what we've found, and I can actually show you a super cool video, is that yeah, the acceleration due to gravity is indeed the same for all objects as they accelerate towards the Earth, if you can indeed remove all the air and prevent air resistance from being an influence. So to show you that, I have a video of Brian Cox in this huge vacuum chamber. What a vacuum chamber is a chamber where you can pump the air out, and they're going to drop a bowling ball and some feathers. Pretty neat stuff. Check it out. So I'm skipping a few parts for the sake of time. You can watch the whole video by following the link from our Foxtail site if you like, but I just want to kind of show the points that we're discussing here. So if you see, the bowling ball crushed the feathers, right? But wait, I thought I just got done saying that all things fall at the same rate. Well, if you notice, Brian Cox is still standing in the vacuum chamber, which means there's still air in there, he can still breathe. And so air resistance greatly influenced the feathers. It influenced the bowling ball as well, but it influenced the feathers much more. Okay, so now what they're going to do is they're going to go ahead and close up the chamber, pump out all the air. It's kind of fun to watch these NASA guys get kind of nerdy. They're going to pump out the air and then drop the bowling ball and the feather again. So check this out. Just so you know, sorry to pause the video again, but just so you know, this video is played in slow motion, okay? So this is not the real-time rate of how this would happen. In fact, I wish they had shown more real-time footage as well as the slow-mo. But anyway, check it out. Look at them fall. Look at that, exactly together. I've watched this video so many times, and every time I just get like goosebumps from it. It's amazing. Look at those feathers, perfectly keeping pace with the ball, both falling down at exactly 9.8 meters per second squared. Look at that, they hit at the exact same time. And that's one of my favorite parts too, just to see these guys working for NASA. Brian Cox, who's an incredible physicist, just so pumped up to see the exact same thing. If we go back just one more time, check this out. The feathers and the bowling ball falling so perfectly together at the exact same time. Oh man, it's so incredible. So in the absence of air resistance, all objects will accelerate towards the Earth at the same rate. And now these things are both falling at 9.8 meters per second squared. So if we watched it in live time, they would both go much more rapidly than what you see here. To show you another really cool video, this is from the moon, all right? And so you'll see here them dropping two objects on the moon. And so part of the reason why it's neat to see this on the moon is because you don't need a big vacuum chamber. There's almost no atmosphere, and so there's almost no air resistance on the moon. So check this out. How about that? Check it out. Here you go, in case you blinked. Boom. One more time. Why not? Oh, one more time. Here we go. Boom. So cool. Again, they fall at the exact same rate and hit the ground at the exact same time. That's a hammer and a feather. Two things to observe. One is that they both hit the ground at the exact same time. The second is they both fall a lot slower than if I were to just drop a, golf ball here on the Earth. Why is that? Well, the moon, being so much less massive than the Earth, has a lesser gravity. So as I just got done saying, the acceleration due to gravity on Earth, approximately 9.8 meters per second squared. On the moon, the acceleration due to gravity is about 1.6 meters per second squared. Interesting. All right, so I want to just wrap up this section once again with kind of a more detailed example problem to show you how we can solve these sorts of problems using our same equations of motion from before, but now investigating and thinking about the idea of free fall. All right, so fleas, those little things that annoy my big dog Gus sometimes, those little insects amazingly can jump vertically about 22 centimeters. So, I mean, this is approximate, but 22 centimeters is probably something like this. It's a pretty substantial distance, probably more than some of us can jump vertically at times. So, anyway, these tiny insects can jump vertically straight up and down 22 centimeters. So I have three questions I want you to try to solve based on just that information I gave you there and ignoring the influences of air resistance. First of all, what is the initial velocity of the flea? Second, what is the velocity of the flea when it lands? And thirdly, how long is the flea in the air? What's its hang time? Okay, so just to clarify, initial velocity, final velocity. Sometimes people get confused with this. It's like, oh, final velocity, he's landed, it must be 0. Well, that's after he's had an outside influence of the ground. And so he has not had a constant acceleration if you include the ground. So anytime you see things like initial and final velocities, that means the instant, for initial, the instant right as he's jumping off the ground. So he's on his way up, but not being influenced by the ground any longer, and still at the very, very lowest point he could be while not being influenced by the ground. And then final velocity is the instant just before he's about to land, right before, boom, but not having been influenced by the ground. So every time I talk about final velocity and these kinds of things, I don't want to see 0. If I launch a ball off of a cliff on a homework problem and I say, hey, what's the velocity right before it gets to the ground, or its final velocity, don't say 0 because I hit the ground. Okay, we're looking at the instant just before that. So pause the video, try this one out, and then we'll solve it together here in just a second. Did you do it? Okay. Hopefully you did. If not, pause it for real. So here we go. Here's our flea. He's going to jump up. Again, I'm following the process. Trust the process, starting with a picture. So he moves up, he reaches his peak height, then he falls back down, returning to where he started. Let's label our variables. I know that my initial position, I'm going to call 0. I know that my final position was the 22 centimeters of vertical leap, or 0.22 meters. That's up at the peak, so I'm going to call that y1. I'm not just calling it final, because really there's 3 points in time we're interested in, right? We're interested at the start, at the peak, and then when he returns back down. And so y2, or the third spot, is when he is back at the 0 position. Labeling my velocities at each of these 3 locations, I have an initial velocity that I don't know, I'm trying to find. I know up at the peak, once we're at max height, as we talked about earlier, the velocity will be 0, and then when he returns back to the ground, that's another thing that we're trying to find. That's really the answers to A and B right there. Looking at other variables, I know that the acceleration the entire time is negative g. So notice here, g just represents the magnitude of 9.8 meters per second squared. So I put in the negative to tell me that it's down, and the amount of time I want to figure out as well. So it looks like there's a lot of things we don't know. Boy, howdy, huh? So let's try this out. I decided to start by looking at my initial vertical jump, just from where I started to the peak. Since I know information about the peak, I don't know about time, so I choose my equation that doesn't depend on time, and I'm going to say, okay, I know that my velocity initial I want, my final velocity up at the top is 0, so 0 squared is 0. My y1 is 0.22 meters, I know that. My acceleration is negative g, and then my initial position is 0. So from there I can solve for my initial velocity. It's just going to be equal to the square root of 2 times g times the initial position. This negative went away because I moved it to the other side of the equation. So if I solve, boom, I find that I have a box-worthy 2.08 meters per second as my initial speed. Guess what? If you were to go through and use any of your equations of motion to solve, you would find that the final velocity, since you're covering the same distance under the same acceleration due to gravity, you'll have the exact same magnitude of velocity when you land back, just opposite in direction. It's the symmetry of uniform motion that we observe and can conclude that the final velocity would just be negative 2.08 meters per second. If you don't trust me, try your equations of motion. Use this same equation with 0 as your initial velocity, negative 9.8 as your acceleration, and your initial position is 0.22 and your final position is 0. You'd solve and you'd get the exact same value that I got right here. So we can conclude that our initial and final velocities are equal in magnitude but opposite in direction. So lastly, to find the last part, we need to determine the amount of time. So we're looking for the total hang time. So I'm starting from the initial position all the way up and all the way back down to my final position. So I'm starting with V initial and looking at V2 as my final velocity. So if I plug in negative 2.08 meters per second for my final, positive 2.08 meters per second for my initial, minus GT, I can find my time is going to be equal to, oh, I think my picture's in the way, so I'll move that. You should find that your time is equal to, boom, a box-worthy 0.424 seconds. All right, so if you have any questions on this, let me know. You'll also see some other sample problems on Foxtail, but other than that, have yourselves a box-worthy day. That wraps up Chapter 2, and we're going to move on to now applying the same stuff in 2 dimensions when we start Chapter 3. Have a box-worthy day.